Okay, let's go. Number 1. The Black Knight Satellite. You're inside Mission Control in Houston. The date is December 1998, and the crew of STS-88 is running a routine spacewalk to assemble the first pieces of the International Space Station. A camera catches something drifting past in the black. Dark, elongated, tumbling slowly against the star field, moving on a path nobody assigned it. NASA's official answer comes fast. Lost thermal blanket. Drifted free during the mission. Case closed. Except the object had already been tracked for decades before that spacewalk ever happened, and a lost blanket doesn't have a flight history. In 1899, Nikola Tesla was running experiments with a high-voltage receiver in Colorado Springs when he intercepted a repeating pattern of radio pulses. Tesla wrote that the rhythm was too structured to be solar interference, too consistent to be noise, and too deliberate to dismiss. He counted the pulses. He timed the gaps. He never identified the source, and the notebook entry still exists, undisputed, in his own handwriting. 55 years later, in 1954, newspapers across the United States ran wire stories quoting Air Force sources describing two unidentified satellites orbiting Earth in a polar path. That's the detail that should stop you cold. No nation on the planet had polar orbit launch capability in 1954. The Soviet Union wouldn't put Sputnik into orbit for another 3 years, and Sputnik's inclination wasn't even close to polar. Something was already circling the poles before humanity had the engineering to put anything into orbit at all. In 1960, the U.S. Navy's Space Surveillance Network and Grumman Aircraft Corporation independently logged a dark, tumbling object in a near-polar orbit, cataloged and tracked using early radar systems built specifically to distinguish artificial objects from natural debris and space junk. Grumman's own internal engineering newsletter reported it as a confirmed tracking anomaly, not a rumor. This wasn't a fringe claim. It was an aerospace engineering firm's official tracking log, filed the same way any other satellite pass would have been filed. Here's what makes orbital mechanics specialists uncomfortable. A thermal blanket doesn't have mass distribution consistent with a rigid, tumbling body holding a fixed rotational period. It doesn't hold a stable, trackable orbit for years at a time. It doesn't show up in radar logs from 1960, 60 years before a blanket supposedly floated away from a shuttle payload bay in 1998, and it doesn't explain a repeating radio pattern picked up 61 years before that. NASA's photographs from STS-88 do match the general shape independent researchers had sketched from earlier radar returns. Dark, elongated, roughly cylindrical, tumbling end over end. But the timeline doesn't match, and NASA's own explanation only accounts for one sighting out of dozens, spanning more than a century of intermittent tracking data. Some researchers connect the object to a 13,000-year-old operational hypothesis floated by amateur radio astronomer Duncan Lunan in the 1970s after he mapped long-delayed echo patterns from 1920s radio transmissions onto a star chart and got a coordinate pattern pointing at the constellation Bootes. Lunan later walked back parts of his own analysis, admitting the star chart correlation was weaker than he'd first claimed. But the delayed echoes themselves, unexplained radio signals that bounce back to Earth seconds after transmission with no known cause, are still logged and still undisputed by the Norwegian physicists, who first recorded them in Oslo in 1927. Nobody has ever produced a terrestrial mechanism that fully explains them. If the Black Knight is real, it isn't a satellite in the way we use the word. It's something that was already up there, already moving in a stable polar orbit before the first human being ever left the ground. Not launched, found. Why would an object launched by nobody choose a polar path, the single most efficient orbit for observing the entire rotating surface of a planet below? Why does the tracking history stretch back to an era when tracking itself was barely invented? And if it's debris, whose? The trail doesn't end in orbit. 3,000 miles beneath the Pacific, something else fell out of interstellar space, and this time nobody argued about whether it was real. They only argued about what was inside it. Number 2. IM-1. You're standing on the deck of a research vessel in the Pacific Ocean, 60 miles off the coast of Papua New Guinea. It's June 2023, and a magnetic sled built specifically for this expedition is dragging across the seafloor 2 miles below, hunting for pieces of something that fell from outside our solar system 9 years earlier. This isn't speculation. The United States Space Command confirmed it in writing, in a document that took years to surface. On January 8, 2014, a meteor roughly 3 feet across streaked through the atmosphere and exploded over the Pacific with the force of about 110 tons of TNT. Government sensors built to detect nuclear detonations logged the fireball, flagged its energy signature, designated it CNEOS 2014-0108, and archived the trajectory data in a routine catalog. Nobody looked at it again for 6 years. In 2019, Harvard astrophysicist Avi Loeb and a graduate student ran the archived numbers and found something the original catalog had missed entirely. The object's velocity relative to the Sun was too high, its trajectory too steep to have originated anywhere within our solar system's gravitational pull. It was interstellar. Faster and more energetic than any known solar system object on record, moving on a hyperbolic path that could only be explained by an origin outside the Sun's gravity well altogether. The math made it, by 3 full years, the first confirmed interstellar object ever detected entering Earth's atmosphere, arriving before both Oumuamua and Borisov. The 2 interstellar visitors, astronomers, had already celebrated publicly as historic firsts. There was one problem. The velocity data precise enough to confirm the object's interstellar origin came from Department of Defense satellites, and that data was classified. Loeb's team couldn't publish a peer-reviewed paper without it, and journals wouldn't accept an unverifiable figure. For 3 years, the formal request sat unanswered inside the Pentagon. Then, in April 2022, U.S. Space Command's own scientific advisor, Lieutenant General John E. Shaw, issued a memo confirming the velocity estimate was accurate enough to verify the object's interstellar trajectory at the 99.999% confidence level. A government agency had confirmed, on paper, an interstellar impact using classified tracking data nobody outside the military had been allowed to see for the better part of a decade. In 2023, Loeb organized an expedition, funded privately rather than through any government or university grant, to drag magnetic sleds across a 15-square-mile stretch of debris field calculated from the fireball's energy output and wind drift models run backward from the explosion point. The team recovered close to 700 tiny metallic spherules, most smaller than a grain of sand, sifted by hand and by machine from tons of seafloor sediment. Lab analysis found something nobody on the team had expected going in. A subset of the spherules showed an anomalous ratio of beryllium, lanthanum, and uranium, an elemental signature Loeb's team labeled BLAU, that didn't match the composition of any known solar system meteorite, any catalogued asteroid, or any existing human-made alloy in international materials databases. Here's what makes the mainstream astronomy community uncomfortable. If the composition is confirmed as genuinely extrasolar under further peer review, and the object's interstellar trajectory holds up against continued scrutiny, these spherules would be the first verified physical material ever recovered on Earth from outside our solar system, sitting in a laboratory drawer at Harvard right now, today, while this video plays. Critics pushed back hard, and not quietly. Some astronomers argued the spherules could be ordinary terrestrial contamination, coal ash, or common micrometeorites that happened to settle on the same stretch of seafloor over years of natural deposition. Others questioned whether the original velocity data, still not fully public even after the memo, was precise enough to rule out a solar system origin with total confidence. But the core fact doesn't move no matter how the details are argued. A military agency confirmed, on the record, that something from outside our solar system hit Earth's atmosphere hard enough to be picked up by sensors designed to detect nuclear weapons, and material recovered from the calculated strike zone doesn't match anything cataloged in our solar system. Why did it take 3 years and a general's memo to release tracking data for a rock that had already burned up and posed zero ongoing security risk? And if the composition holds under further peer review, what kind of object, natural or built, produces that exact elemental signature? The fragment stayed behind. The next visitor didn't. It passed through, sped up on its way out for reasons nobody has ever fully explained, and vanished before a single spacecraft on Earth could reach it. Number 3. Oumuamua. You're at the Pan-STARRS telescope on Haleakala, Hawaii, on the night of October 19th, 2017, watching a faint point of light crawl across the frame in a way nothing in the survey's catalog has crawled before. It's moving too fast, on a trajectory too steep, to belong to our solar system, and the automated detection software flags it within hours. Astronomers name it Oumuamua, Hawaiian for scout, or messenger reaching out from the distant past. It's the first interstellar object ever confirmed passing through our solar system, and within weeks, it stops making sense to the people studying it. Follow-up observations from telescopes across 4 continents measure its brightness swinging by a factor of 10 as it tumbles, once every 8 hours, which means its shape has to be extreme to produce that swing. Astronomers model it as 10 times longer than it is wide, either a cigar, roughly 800 feet long, or in later reanalysis, a flattened pancake, up to 300 feet across, and barely 3 feet thick. No confirmed natural object anywhere in our own solar system comes close to that ratio. Not an asteroid, not a comet nucleus, nothing cataloged in over 2 centuries of observation. Then, the object does something a comet does, and something a comet cannot do at the same time. As it left the solar system, telescopes measured a small but statistically undeniable extra push, a non-gravitational acceleration. The same signature comets show when trapped gas venting from their surface acts like a small natural thruster. Except Oumuamua showed no coma, no dust trail, no gas cloud, nothing a spectrometer could detect in any wavelength astronomers checked. An object accelerated exactly like it was outgassing, while displaying zero physical evidence that it was outgassing anything at all. Here's what makes the case uncomfortable for a clean, tidy explanation. A team of mainstream astronomers proposed the acceleration came from hydrogen ice, sublimating in a way too faint for any instrument to detect directly, a mechanism nobody had ever observed on another object, but that would resolve the puzzle mathematically if it turned out to be true. Harvard's Avi Loeb, the same physicist who later chased the interstellar meteor fragments off Papua New Guinea, published a peer-reviewed paper in 2018, arguing the data fit more cleanly with an artificial origin. A thin, artificial solar sail, he argued, would explain the extreme brightness variation, the flattened shape, and the non-gravitational acceleration all at once, without inventing an entirely new, never-before-seen ice composition just to make the numbers work. He was careful to frame it as a testable hypothesis, not a conclusion, but the paper still triggered public pushback from colleagues who called the idea premature and unnecessarily provocative. The object was only observable for 11 days before it grew too faint to track, moving at roughly 58,000 miles per hour on its way out of the solar system, never to return, never intercepted, never sampled by any spacecraft. No mission on Earth existed fast enough to reach it in the brief window. Humanity had it in view, and by the time any proposal to chase it was even drafted, it was already gone. Astronomers remain divided years later. The ice sublimation model has never been directly confirmed for this specific object, because the ice itself was never detected. The artificial light sail model has never been ruled out, because the acceleration data still has no confirmed natural cause. Why did the only confirmed interstellar object ever observed happen to pass within reach of our telescopes for barely a week and a half? Why did it wake up, accelerating only once it was already leaving, past the point where any spacecraft could possibly catch it? And why, years after Borisov, the second interstellar object, arrived showing the ordinary visible tail of a comet exactly as textbook physics predicted, does Oumuamua remain the only interstellar visitor that broke the pattern completely? While one object drifted quietly out of reach forever, something closer to home has been sitting in plain sight the entire time, orbiting a planet we've mapped in detail for 50 years, hiding a number that shouldn't be possible. Number 4. Phobos. You're in a cramped Soviet observatory office in 1959, watching astrophysicist Iosif Shklovsky run the same orbital calculation for the 3rd time, hoping for a different answer. He isn't getting one. Phobos, the larger and closer of Mars's 2 moons, is spiraling inward toward the planet at a rate that shouldn't be physically possible for a solid chunk of rock its size. Shklovsky's numbers point to only one explanation that fits the observed decay rate cleanly. Phobos would have to be hollow, its density low enough that atmospheric drag and tidal forces are dragging it toward Mars decades faster than any solid natural satellite should fall under the same conditions. He publishes the hypothesis anyway, fully aware of what it implies for a Cold War scientific establishment already primed for space race paranoia. A hollow moon isn't captured by a planet's gravity in the ordinary sense. It's built. The claim doesn't fade quietly into academic footnotes. Spacecraft sent to Mars over the following decades keep finding details that make the picture stranger, not simpler. Mariner 9, arriving in 1971, photographs Phobos up close for the first time in human history and reveals dozens of long, parallel grooves scarring its surface, some running for miles in near-perfect straight lines across curved terrain. Impact cratering, the leading natural explanation offered at the time, doesn't easily produce grooves that parallel each other so consistently. Some researchers have proposed the grooves are stress fractures radiating from the impact that created Phobos's largest crater, Stickney, nearly 6 miles wide, but the alignment pattern doesn't match standard fracture mechanics cleanly across the entire surface. Then, in 1988, the Soviet Phobos 2 probe transmits a final set of images before contact is lost for good, showing what mission scientists describe internally as an elongated shadow on the Martian surface near Phobos's position, roughly 12 miles long. That doesn't match any known geological feature or known imaging artifact. The probe fails completely 2 days later, the second Soviet Phobos mission lost in as many attempts within a single decade. Here's what makes planetary scientists uncomfortable saying out loud at conferences. Later spacecraft measurements refined Phobos's density to roughly half that of solid rock, low enough that mainstream science now attributes it to a loosely packed rubble pile structure, a body assembled from captured asteroid debris riddled with internal empty space rather than a machined hollow shell. That explanation accounts for the low density reasonably well. It does not fully account for the parallel grooves running in coherent lines across curved terrain, and it does not explain why Phobos's orbital decay rate, even under the rubble pile model, still runs measurably faster than comparable captured moons observed around other planets in the solar system. In 2011, Russia launched Phobos Grunt, an ambitious mission to land on the moon and return a soil sample to Earth, the first Mars system sample return attempt in history and a point of national pride. The spacecraft's engines failed to fire minutes after reaching orbit. It never left Earth orbit, tumbled uncontrolled for 2 months while engineers scrambled for a fix, and crashed back into the Pacific Ocean. In January 2012, the third failed Phobos mission in a row, following the 2 lost Soviet probes 20 years earlier, almost to the month. 3 missions aimed at the same 11-mile-wide moon. 3 failures. Officially, coincidence, and space missions fail constantly for mundane reasons involving cheap components, software errors, and tight budgets. But researchers who track the pattern ask why Phobos specifically carries that record when missions to far more distant and technically demanding targets, including Pluto and interstellar space itself, have succeeded on the first attempt. Is the rubble pile model the full answer, or does it only explain the density and leave the grooves and the decay rate unresolved? What did Phobos 2 photograph in its final hours before contact was lost for good, and why has that image never been fully released for independent analysis? 1,400 light-years from that silent moon, a star was doing something no planet could explain, dimming and brightening in patterns that looked less like nature and more like something engineered, slowly coming apart. Number 5. Tabby's star. You're a volunteer on the Planet Hunters Citizen Science Project in 2015, scrolling through NASA Kepler telescope, light curves at your kitchen table, when you flag a star that doesn't look like anything in the training examples you've been given. Its official name is KIC 8462852. It will soon be known as Tabby's star, after Yale astronomer Tabitha Boyajian, who leads the team that investigates what you just found. A normal planet passing in front of its star blocks maybe 1% of the light, in a clean, repeating, perfectly periodic dip that any first-year astronomy student could model. This star dims by up to 22%, in irregular pulses that don't repeat on any detectable schedule, in patterns too asymmetric and too deep for any planet or any combination of planets to produce. Something is blocking nearly a quarter of this star's total light output at random intervals, and nobody can say with confidence what. Boyajian and astronomer Jason Wright publish a 2015 paper laying out the full range of possibilities, and they include, explicitly and on the scientific record, one they can't yet rule out. A Dyson swarm, a hypothetical megastructure network built by an advanced civilization to capture a star's energy output directly, the way physicist Freeman Dyson first proposed in a theoretical 1960 paper published in the journal Science. Wright is careful. He frames it as the least likely explanation on the list, not the leading one, and insists it be tested like any other hypothesis by looking for evidence that would confirm or kill it outright. Here's the detail that gets left out of most retellings. A functioning Dyson swarm, one still being assembled and maintained by whoever built it, should dim its star in a slow, orderly, increasingly structured way, as more collector panels lock into a stable configuration over time. That is not what the data shows. Some analyses find no infrared excess strong enough to match a natural dust cloud of the size needed to explain dips this deep, which rules out simple debris, but the dimming itself keeps getting messier, not cleaner, dip after dip. Here's what makes the astronomical community uncomfortable. Digitized photographic plates dating back to 1890 show the star has also dimmed gradually and steadily, about 14%. Over the past 100 years, a slow, secular fade layered underneath the sudden sharp dips, as if something that was once whole is coming apart in stages rather than being built up. In 2017 and 2018, a coordinated citizen-funded observation campaign, backed by a Kickstarter that raised over $100,000, specifically to keep telescopes trained on the star during a predicted dimming event, captures new dips in real time and finds they dim unevenly across different colors of light, more in blue wavelengths than red, a signature more consistent with fragmenting, unevenly sized debris than with an intact reflective structure. Most astronomers now favor an uneven cloud of orbiting debris as the explanation, and they may be right. But debris from what? A dust cloud that dense, irregular, and asymmetric, with no matching parent comet or collision event ever identified, and with a 100-year decline layered on top of it, looks less like a nursery for something being built, and more like the wreckage field of something that already was. Why does the star keep dimming on no fixed schedule, in a pattern that grows more chaotic rather than more orderly, 9 years after the anomaly was first flagged? Why does the century-long fade track a slow collapse rather than a slow construction? And if something was built here, why has nothing collected, repaired, or replaced a single piece of it in over 100 years of observation? 10 light-years from us, a signal came from a star even closer than Tabby's, one that fired exactly once and then, despite years of listening, never made a sound again. Number 6. BLC1. You're at the Parkes Observatory in New South Wales, Australia. In April 2020, during 26 hours of dish time pointed directly at Proxima Centauri, the nearest star to our Sun, just over 4 light-years away. The Breakthrough Listen project isn't hunting for anything specific that week. It's running a routine survey. Then the software flags something that passes every filter designed to catch false positives, and it doesn't get thrown out. A narrowband radio signal, centered at 982 MHz, a frequency with no assigned civilian or military use anywhere near that band. It's designated BLC1, Breakthrough Listen Candidate 1, and it does the one thing SETI researchers spend entire careers hoping to see just once. It appears only when the telescope points at Proxima Centauri, and it vanishes completely when the telescope points away to a reference position nearby. That's the gold standard positive detection test, the same protocol used to validate or kill every SETI candidate since the field began, and this signal passed it cleanly. There's more. The signal's frequency drifts slightly over time, and the drift rate is consistent with what you'd expect from a transmitter sitting on a rotating, orbiting planet, not a fixed source anywhere on Earth. Proxima Centauri has a known planet, Proxima b, a rocky world sitting inside its star's habitable zone. A signal, from the direction of the nearest star system to our own, with a drift rate matching a planet astronomers already know is there. Here's the part that gets buried under the controversy. This wasn't a conversation. It was one transmission, 26 hours long, and then silence. Breakthrough Listen has logged more than 1,000 hours of dedicated follow-up observation time on Proxima Centauri since 2020, using multiple instruments, at multiple frequencies, specifically hunting for a second occurrence. Nothing has ever repeated. No SETI program anywhere on Earth has detected it again, not once, in years of continuous listening aimed at the exact same coordinates. A civilization actively broadcasting, running an ongoing communication effort, does not transmit for 1 day out of 5 years and then go completely dark forever. That pattern fits something else better, a single automated pulse, an old relay or beacon triggered once by a passing event, a navigation ping from hardware that has been drifting unattended for who knows how long, or the final gasp of a transmitter losing power for the last time. Breakthrough Listen's own team sat on the detection for 5 months before it leaked to a British newspaper in December 2020, running internal checks to rule out human interference before saying anything publicly. In October 2021, the team published a peer-reviewed paper attributing BLC-1 to radio frequency interference generated by human electronics on or near the observatory, though the paper never named the specific device responsible. The interference explanation may be correct, but if the signal was real, and it did come from Proxima Centauri, the silence that followed is the detail that matters more than the signal itself. Why would a functioning, actively used transmitter broadcast exactly once in 5 years of continuous monitoring? And if it wasn't interference, was that single burst the last transmission of something that simply stopped working, sent by whoever built it long before anyone on Earth owned a radio telescope capable of hearing it? One signal from one star, fired once and gone, is easy enough to dismiss as noise. But a team of astronomers wasn't looking at single stars anymore. They were scanning 100,000 entire galaxies, looking for the leftover heat of machines nobody was running anymore. Number 7. The WISE Survey. You're in a windowless office at Penn State University in 2015, part of a research team sorting infrared readings from 100,000 galaxies, one at a time, looking for something specific and deeply strange. Not planets, not stars. The leftover heat of engineering too large to ever fully switch off. In 1960, physicist Freeman Dyson proposed that any civilization advanced enough to outlast its own home star would eventually need more energy than one planet could ever supply, and the only place left to get that much energy is the star itself. A civilization that wrapped a star in solar collectors, a Dyson swarm, wouldn't be visible in ordinary visible light because the entire point of building one would be to capture nearly all of it. But physics doesn't allow energy to disappear cleanly. Captured starlight has to go somewhere, and it comes back out as heat, specifically as mid-infrared radiation, a very particular wavelength signature that an ordinary star doesn't produce on its own. Astronomer Jason Wright, the same researcher who investigated Tabby's star, leads a project with the acronym GHAT, the Glimpsing Heat from Alien Technologies Survey, using archived data from NASA's WISE Space Telescope to search, not for one anomalous star, but for entire galaxies radiating more waste heat than stars and interstellar dust alone can reasonably explain. If even a small fraction of the stars inside a galaxy were once wrapped by a sufficiently advanced civilization, that galaxy's total infrared output would tilt measurably away from what standard astrophysical models predict. The team screens the full sample and finds the overwhelming majority behave exactly as expected. But a small number, roughly 50 galaxies out of the 100,000 screened, show infrared excess strong enough that the team can't fully explain it using known galactic processes, star formation bursts, dust density, or measurement error. Here's the detail that separates a live signature from a dead one. A civilization still actively operating a stellar-scale harvesting network would show that excess heat tracking its energy consumption in a structured, patterned way, rising and falling as the network expands or is maintained. What the flagged galaxies show instead is a flat, undifferentiated infrared glow, the kind physicists associate with waste heat radiating passively off inert material, not with an active system doing ongoing work. It looks less like a civilization currently running the lights, and more like a structure still slowly bleeding out the heat it absorbed while it was. Here's what makes the finding uncomfortable to sit with regardless. The researchers are explicit that natural explanations remain more likely for every flagged case, and they publish the results exactly that way, hedged, cautious, a short list of outliers worth a second look. That second look never came. No large-scale follow-up survey was ever funded to individually investigate the 50 flagged galaxies in detail, and the project's public visibility faded within a few years, cited occasionally, but never expanded into the dedicated observation campaign its own authors called for. If even one of those 50 anomalous galaxies is real, the implication isn't a thriving civilization broadcasting its presence. It's the opposite, a structure large enough to reshape a galaxy's entire energy budget, still radiating the heat it captured decades or millennia ago, with nothing detected anywhere in the data suggesting anyone is still tending it. Why does a search, explicitly designed to find the most extreme possible evidence of engineered structures, find heat signatures that look abandoned rather than active, and never receive the resources for a closer look? And if the process that built these structures is long finished, what exactly is still radiating that heat, decade after decade, with no one left to shut it off? From 100,000 galaxies scattered across the sky, the trail comes back down to Earth's own front yard, to a photograph NASA took of the planet next door and never fully managed to explain away. Number 8. Cydonia. You're in a JPL image processing lab in July 1976, watching a downlinked frame from the Viking 1 orbiter resolve line by line on the monitor. It's a routine pass over a region called Cydonia, cataloged for its unusual mix of mesas and shallow depressions. Then the shadows fall right, and a mile-wide mesa resolves into something with two symmetrical eye sockets, a ridged nose, and a mouth, staring straight up at the camera as if it had been waiting to be photographed. A NASA scientist, briefing the press days later, calls it a trick of light and shadow, and the agency releases the image publicly anyway, with that explanation attached from the very start. Here's what makes the case harder to close than the official line suggests. Independent researchers spend the following 2 decades studying not just the face, but the wider Cydonia region surrounding it, and one of them isn't an easy voice to dismiss as a fringe hobbyist. Errol Torun, a cartographer working for the Defense Mapping Agency, runs a formal geometric analysis in the early 1990s on a nearby 5-sided mesa researchers, nicknamed the D and M Pyramid. Using standard surveying methods identical to those used for terrestrial mapping, Torun measures the formation's internal angles and finds a pattern of mathematical relationships between them, ratios tied to pi and the golden ratio. Repeating across the structure's geometry more precisely than his own statistical models predict natural erosion should ever produce by chance. He publishes the analysis through the Case for Mars conference, a legitimate aerospace engineering forum attended by working scientists, not a fringe outlet. In April 1998, and again in April 2001, NASA's Mars Global Surveyor orbiter re-images Cydonia at far higher resolution than Viking 1 ever achieved, at NASA's own invitation, specifically to settle the public question once and for all. The new images, taken under a different, higher sun angle than the original 1976 photograph, show a heavily eroded natural mesa with none of the symmetrical facial shadow pattern visible in the original frame. NASA declares the face a natural landform. The case closed for good, and most major outlets reported exactly that way. Skeptics of that conclusion point out something the press releases didn't emphasize at the time. A face defined entirely by shadow geometry, the way the original image showed it, will inherently look different, and can be made to look completely different when photographed under a different lighting angle at a different time of the Martian year. That's not proof the formation is artificial, but it does mean the follow-up images, taken under conditions that would predictably soften the original shadow pattern, don't actually rule out what the original lighting revealed in the first place. The D and M pyramid's underlying geometry, the specific angles Torun measured by hand, remain present in the higher resolution data regardless of sun angle, and no agency or academic team has published a direct angle-by-angle rebuttal of a trained cartographer's formal geometric survey using his own methodology. Why did NASA re-image the most famous formation in Cydonia under lighting conditions that would flatten the very feature under public debate? Why has no agency published a rebuttal of a cartographer's formal geometric survey rather than simply declaring the case closed in a press briefing? And in a region with a humanoid face and a 5-sided pyramid within a few miles of each other, at what point does trick of light stop covering every unusual formation in the same 3-mile radius? The stones on Mars stay silent no matter how long you study them. But 3 billion light-years away, something has been firing the same signal on a fixed mechanical clock for more than a decade, like a machine that never got the order to stop. Number 9. FRB 121102. You're in the control room at the Arecibo Observatory in Puerto Rico in November 2012, watching a burst of radio energy hit the receiver and vanish in under 5 milliseconds, gone before anyone in the room can even react. Fast radio bursts had only been confirmed as a real astrophysical phenomenon 5 years earlier, and every single one recorded up to that point had done the same thing. Flash once, from somewhere impossibly far away, and never repeat. This one breaks the pattern. In 2015 and 2016, the same patch of sky fires again, and again, dozens of times, from the exact same source. Astronomers designate it FRB 121102, and it becomes the first confirmed repeating fast radio burst ever found. Using very long baseline interferometry, researchers trace the burst to a small, faint, dwarf galaxy, roughly 3 billion light-years from Earth. Each individual pulse releases more energy in a few milliseconds than the Sun produces in an entire day. In 2017, Harvard's Avi Loeb, joined by astrophysicist Manasvi Lingam, publishes a peer-reviewed paper modeling what kind of source could physically produce bursts with this exact combination of energy, polarization, and repetition. Their conclusion is narrower and stranger than a simple broadcast. The paper shows that a transmitter, roughly the size of a large planet, powered by a star, generating a tightly focused beam for the specific purpose of driving a giant light sail across interstellar distances, would produce a signal with almost exactly this profile. Not a message meant for us. A propulsion system, running on automated schedule, doing the one job it was engineered to do, whether or not anyone is still around to use it. Here's the detail that changes how you should read this signal. In 2020, researchers analyzing years of accumulated observations find the bursts aren't randomly repeating at all. They cluster into an active window lasting about 90 days, followed by a silent window of roughly 67 days, a cycle repeating with a period of approximately 157 days, tracked consistently across years of data. That kind of clean, mechanical periodicity is not the signature of a conversation. Nobody answers a call, pauses for exactly 2 months, and calls back on a fixed clock, over and over, for a decade straight. That's the signature of a machine, a system running on a timer it was built with, indifferent to whether there's still a hand on the switch. The leading natural candidate, a magnetar, a young neutron star with an extraordinarily powerful magnetic field, fits much of the data, but has never been observed anywhere else producing a cycle this precise. If Loeb and Lingam's model holds, even partially, what's firing across 3 billion light-years isn't a civilization greeting the galaxy. It's hardware, still following its programming, long after whatever built it stopped checking in. Why does a source out of thousands of one-off flashes repeat on a cycle this mechanically exact? And if it is engineered, why does it behave like an unattended system running out its schedule rather than a signal aimed at being heard? Every one of these signals, these fragments, these silent stone faces, traces back to a single case file that started the entire search, one nobody has ever managed to close. Number 10. The wow signal. You're sitting beside astronomer Jerry Eman at Ohio State University on the night of August 15, 1977, watching a wide-format printout scroll out of the Big Ear radio telescope's line printer, one row of characters at a time. The telescope isn't steerable. It scans a fixed strip of sky as the Earth rotates beneath it, and for exactly 72 seconds, the maximum time any fixed point of sky could remain in its field of view, it holds a signal at 1420.4 MHz, a frequency locked to the natural emission of neutral hydrogen, the single most abundant element in the entire universe. In 1959, physicists Giuseppe Cocconi and Philip Morrison had proposed that exact frequency years before anyone detected anything unusual there, as the single most logical, hailing frequency any spacefaring civilization would choose to broadcast on, because any species anywhere capable of radio astronomy would already know that number from its own physics. The signal that shows up 18 years later sits almost precisely on it, within a fraction of a percent. It registers at 30 times the background noise level, strong enough that Eamon circles the alphanumeric code on the printout in red pen and writes a single word beside it in the margin. Wow! The signal was pointed toward a patch of sky near the Chi Sagittarii star group, close to the direction of the galactic center, in a region containing several sun-like stars within a plausible observing distance. It filled the entire 72-second window. Big Ear's fixed dish could hold on any single point before the sky rotated past it and out of range. It never came back. Hundreds of follow-up observations, some using the exact same telescope in the years before it was decommissioned, some using far more sensitive instruments built decades later, have pointed at that same patch of sky again and again, across 5 decades of dedicated search time. Nothing has ever matched it. No satellite, no aircraft, no piece of terrestrial hardware has ever been conclusively identified as the source, despite an investigation that has now run for close to 50 years without a resolution. In 2017, a researcher proposed that a passing comet, releasing a cloud of hydrogen gas as it approached the sun, could explain the signal's frequency and strength. The theory made international headlines for a week, presented as the mystery finally solved after 4 decades. Then Jerry Eamon, the same man who circled the signal in 1977, publicly and directly refuted it, pointing out that comets don't produce narrowband radio emission at that frequency or anywhere close to that strength, and that no comet observed before or since has ever been shown to replicate the signature in any subsequent test by any observatory. The explanation didn't hold up under its own math, and the researcher who proposed it never published a peer-reviewed follow-up defending it. Jerry Eamon died in 2023, having spent close to half a century fielding the same question from journalists, students, and strangers, and never once claiming to know the answer for certain. He remained publicly certain of only one thing until the end of his life. It was real, it was strong, and it hit the one frequency physics itself had already flagged as the most likely channel for contact, decades before anyone on Earth was even listening for it. Why does the strongest unexplained signal ever recorded sit precisely on the frequency 2 physicists predicted on theoretical grounds alone 18 years before it arrived? Why, across nearly 50 years and thousands of hours of dedicated follow-up observation time, has that exact patch of sky never produced anything like it again? And why did the one man who spent his career trying to close the case die, still calling it open? 10 traces. 5 continents worth of telescopes and observatories, and 5 decades of tracking data spanning an object tumbling in polar orbit before satellites existed, fragments recovered from an ocean floor, with an elemental signature nothing in this solar system produces, a star coming apart in patterns that look like collapse rather than construction, a signal that fired once in 5 years and never again, a beacon still firing on a mechanical schedule with no one answering it, and a signal locked to the one frequency physics itself, predicted decades before it arrived. Notice what almost none of these traces actually are. They aren't conversations. Nobody transmitted, waited for a reply, and transmitted again. What we have instead is wreckage, silence, and machinery still running out its programming with nothing behind it anymore. A dark satellite tumbling in an orbit nobody has corrected in a century. A megastructure radiating heat, it captured long ago with no one left to maintain it. A beacon firing on a clock its builders set, and then, as far as anyone can tell, stopped resetting. Individually, mainstream science has a plausible answer ready for every single one of them. A lost thermal blanket, a dust cloud too faint to fully image, a rubble pile assembled from captured debris, terrestrial radio interference from an unnamed device, a trick of light, and a convenient sun angle. Each explanation, taken alone, sounds reasonable, even likely, but look at what each of those explanations has in common. Every one of them was proposed once, stated with confidence in a press release or a hedged paper, and then never chased down a second time with the follow-up funding, the second expedition, or the dedicated instrument time its own discoverers explicitly asked for in their own published conclusions. The interstellar meteor's classified data sat unreleased for 3 years. The WISE survey's 50 anomalous galaxies never got a second look with better instruments. The Proxima signal took 5 months and a press leak to even become public. That's not a pattern of active cover-up in the cinematic sense. It's something quieter and, in its own way, more unsettling. A pattern of institutions, asking the right question once, getting an answer that doesn't fit comfortably into an existing model, and simply not asking again. 10 cases. 10 unfinished files. If even one of them is what its most careful researchers say it could be, it isn't proof that something out there is still watching us back. It's proof that something was, once, and that whatever built it is long past answering. This video walked through 10 of the most carefully documented, most rigorously argued anomalies in modern astronomy, from a satellite tracked before Sputnik existed to a radio signal still unexplained after 50 years, and every one of them remains officially open, unresolved, and quietly under-investigated. If you want more deep dives like this, subscribe, drop a like, and tell us in the comments where in the world you're watching from.